So before Christmas, we talked about interference patterns. Okay, we talked about linear superposition, okay, all of that kind of stuff, constructive interference and destructive interference. We talked about wave behavior at a boundary. Okay, so when a wave hits a fixed end, that's like an infinitely dense medium, and it will reflect back. But how will it reflect? Anybody remember?
Inverted.
Inverted. So if it was coming in as a crest, it's going to hit that and come back as a trough. Everybody with me there? Okay, so that's what we're talking about. Okay, so standing waves are the result of a whole bunch of waves on or in a medium that are just continuing to travel back and forth on that medium, reflecting off of one end and coming back to the source. The source continues to make waves, and if all those waves are identical, that is, they have the same frequency, speed, and wavelength, which they would, okay, they will start to make a pattern on the medium or in the medium, okay, as they travel. Okay? And that's simply because they're going to interfere at the same places, okay, because they all have the same wavelength. They all have the same frequency, and because they're in the same medium, the same speed. Okay? It's how most musical instruments work. Okay? We create a resonance of some kind, okay, that produces a sound that amplifies itself. Okay? That's how all acoustic instruments work. An electric guitar works differently because it's a powered amplifier. Okay? But if I'm playing an acoustic guitar, I'm using standing waves and resonant waves and things like that to produce a sound. Everybody okay with that idea? Okay. So, standing waves are, okay, the result of repeating patterns of interference. Okay? We're going to look at how those patterns are formed, and we're going to learn the proper names of areas of constructive and destructive interference, and we're going to look at resonating columns of air, okay, or resonance columns. Okay, I need somebody to hold the other end of my spring. Jim is experienced, so that's good. Okay, and we're going to stand up for this one. So you're good right there. Okay, so if I start making waves towards Jonah, okay, Jonah's acting as a fixed end for me, okay, this is the first standing wave pattern that will form on the spring. Okay, because I'm just continuing to make the same wave over and over again. Okay, how much is my hand moving? Very little, but how much is the spring moving in the middle? Where is it getting all the energy from if my hand's only moving this far?
The reflection.
Exactly. It's interference. What kind of interference is happening at the middle? Constructive. That's why the amplitude's getting bigger, right? It's constructing a larger wave. So all the waves are arriving as crests together or troughs together at the center. That's where the pattern of constructive interference is, or the point of constructive interference is. What kind of interference is happening right at Jonah's hand? Destructive, because at Jonah's hand, everything turns into its exact opposite, right? That's where the reflection that inverts the wave happens. The same thing happens here in front of my hand. Okay? My hand is the source, but also it's a fixed end. So it reflects off of here as well. So we have a point of destructive interference, a point of destructive interference, and a point of constructive interference in the middle. Okay? How many wavelengths are on this spring right now?
2.
Half.
Oh, because it's
Right? There's not a full cycle, right? There's no full cycle on here. Okay? Now, if I shake this spring twice as fast as I was just shaking it, what's it going to look like? One full cycle. How many points of constructive interference will there be? Okay, so now I've got 2 points of constructive interference. What's in the middle now? The point of destructive interference. Okay, but I'm shaking this at twice the frequency I was shaking it before, which means I shortened the wavelength. Right? And by shortening the wavelength, I made one full cycle fit on the spring. What happens if I shake it 3 times as fast as I shook it initially? I'll get 3, right? How many wavelengths are on here? 1 and a half, yeah. Okay, if I shake it 4 times, I'm going to start to work up a sweat. But It's hard to maintain it. Is that 5?
Might have been.
Oh, I thought I only counted 4. It's hard to go any faster than that. Thanks again. Okay, so we got those standing waves. Okay, that's what standing waves look like. Okay, so a standing wave is an effect. It isn't really standing. The pattern stands, but the waves are actually moving back and forth. Okay, so standing wave is kind of a misnomer, kind of a bad name. Okay, the pattern stands still, but the waves are moving back and forth. Okay, so it happens when 2 or more waves travel through the same space at the same time. Pattern is the result of both kinds of interference. Okay, so this is exactly what we had on the spring. We had our first standing wave, our second standing wave pattern, and our third standing wave pattern. And we found that this one and this one were multiples of the first. Okay? The frequency I had to shake the spring at had to be twice as fast in order to get the second pattern. Okay? Twice as fast because I had to half the wavelength in order to get it to form. So for any medium, there are only a certain number of frequencies that will actually form these wave patterns. You can see that when I was trying to get the fourth one, I was struggling, okay, because I couldn't find that frequency. Okay, it was much, much harder. It's really easy to find the first few. Okay, but after that, it's so fast that you're not as exact in how you shake the spring, so it's hard to find that exact frequency. Okay, so only some frequencies will actually form the patterns. Okay, that has to do with the medium itself, okay, and the number of waves that can fit on it. Everybody okay with that idea? All right, so if this was 100 hertz, which obviously it wasn't, okay, let's say it was, what would this one be? 200, and this one would be 300. So that's what we got to realize. All the frequencies that produce these are going to be multiples of the first. Okay, so this one here we call the first harmonic. Harmonic. Yep. Okay, or the fundamental. Struggling. Okay, first harmonic frequency or the fundamental frequencies. Fundamental because everything is going to build on that one. Okay, this is our second harmonic. And this is our third. Okay, and that system works very well because it also happens to coincide with the number of areas of constructive interference that appear on the medium. Okay, so here's kind of an easy question that I might ask as a multiple choice problem on, let's say, a unit exam on Tuesday of next week. Okay, if this distance here is 1.5 meters, what's the wavelength of this pattern?
Would it be 3 meters?
It would be 3 meters because this represents half of a wavelength. Okay, what's the wavelength of this one? 1.5. What's the wavelength of this one?
1.
Okay, well, there's 1.5 wavelengths here, right? So in 1.5 meters, there are 1.5 wavelengths. So the wavelength would be 1 meter, yes?
Yeah.
Okay. Everyone all right with that? Okay. That would be the kind of question I might ask. You have a standing wave pattern that has 3 areas of constructive interference, which we call antinodes. And it is this many meters long. What's the wavelength? And you have to figure it out. Okay? All right. So this is what we did. Obviously, we made these. The terminology that we have to learn, okay, is the term for the areas of constructive interference and the term for the areas of destructive interference. right? So any place where the displacement is 0, that is, it's not moving, destructive interference is occurring, is called a node. Okay, so these points right here, 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 and there, okay, are all nodes. Yes. Okay, they are areas where destructive interference is occurring and there's no displacement. Okay, everybody all right with that? Okay. Now, an area where there's constructive interference is the opposite of that. So it's an antinode. Seems like they could have come up with a better name, but that's what they called it. Okay, so an area of complete constructive interference is known as an antinode. Okay, and then again, we have these labels here. So our first standing wave pattern is our fundamental frequency, okay, our first harmonic, okay, and then our second one is our second harmonic. We do not use these terms because they're very, very confusing and people get them mixed up. Okay, so we don't use these overtone terms, okay, because they don't coincide with the number of antinodes. So the first harmonic frequency has one antinode, it's the fundamental frequency. The second harmonic has two antinodes, okay? Third harmonic has three antinodes, and so on. Okay. Everybody all right with that? Okay. Okay, so each standing wave pattern is produced at a unique frequency. We talked about that already. That's why it was so hard for me to get the fourth pattern, okay, since I just couldn't seem to arrive or find that frequency exactly. Okay, so it's produced at a unique frequency, and those frequencies form a series. The smallest F1 has a single antinode. That would be this one. Okay, and again, I said I don't use the overtone terms. Okay. All right, and they are, of course, multiples of each other, and that's how we produce musical octaves, okay, in music. So if you had, like, middle C, the next C up would be the next frequency, the next harmonic frequency, and so on and so on. Okay. All right. Questions on that? All right, so standing wave patterns arise because identical waves travel along the spring or whatever the medium is, okay, and they combine according to the principle of linear superposition. Now, sometimes we want to take advantage of that, and sometimes we want to prevent it at all costs, okay? In most cases that are not involving music, we don't want standing waves to form, because if they do, they are going to result in large movements of the medium. The medium could include things like buildings, bridges, and things like that. If I get a standing wave forming in a building, the building will collapse. Okay, so for example, in downtown Calgary, all of the big skyscrapers are designed to sway slightly. Okay? Because if they weren't, they would break and fall down in strong winds. Okay? Some people are especially sensitive to this. Okay? Like my wife used to work at downtown Calgary, and there were days that some people just went home. If we had a big Chinook going on, the building would move like this, and if you were near the top and you were sensitive to it, you could get motion sickness sitting at your desk. Okay? It's not a lot. I'm not saying like people are like, whee, at the top on their, standing on their desk pretending they're surfing. Okay? It's not like that at all, but it's enough for people who are especially motion sensitive to feel it and feel nauseous as a result. Be no different than if you were on a boat in a rough sea. Okay? So they're designed to move a little bit, but if those waves are allowed to go to the top of the building, they'll reflect off the top of the building and they'll travel back down. Okay, and then they'll reflect off the ground, and they'll keep doing that, and they'll keep getting put in there because the wind keeps pushing on the building. And all materials have some aeroelastic property, which will bring them back to their original shape, except if I start to get a simple harmonic motion occurring in a building like this, okay, and those waves never leave, the building will start to experience constructive interference in a few places, and that will result in it coming down. Okay? So what they typically do is the pilings are built, okay, so the things that the building sits on are built so that there's different amounts of resistance on different sides of the building. So waves travel faster on one side than they do on the other, and so they can never set up a constructive interference or a resonant frequency. They can never resonate, so the building can't just start going back and forth like this and fall down. Okay? This was something they overlooked when they built the Tacoma Narrows Bridge. Okay? The Tacoma Narrows Bridge went across this kind of sound, Deep River Canyon, in Tacoma, Washington. And days after it was built, the wind came up, and the bridge started doing this, which it was totally designed to do. All suspension bridges are designed to sway a little bit. I mean, after all, they're built with big cables. Okay, so they're designed to move a little bit. The problem was they got a sustained wind for several days that didn't change. So the same wind speed kept pushing on the bridge in exactly the same way for days on end. And what happened was, instead of the bridge doing like this, like it was designed to, there started to be basically a vacuum produced on one side when there was a huge force on the other. And it started the bridge doing something they never ever envisioned happening. Okay? And as a result, the bridge collapsed. So I'm going to show you the videos of the bridge here. Okay, so they get this standing wave that forms on the bridge. Okay, and it just continues to travel back and forth, so the amplitude of that motion gets bigger and bigger and bigger. Okay, so they rebuild the bridge. But it's 52 years later before they figure out why it collapsed. It never collapsed again. They built it slightly differently, and they build now all suspension bridges this new way. What do you suppose they changed? The bridge doesn't really look any different, but they changed one small thing. Nope. Bridge is still the same width. It has to fit between the stanchions, right? Between the big ends of it there.
Either like the depth of the bridge, like this way, or it's something at the ends that would absorb the motion.
It is something at the ends.
Did they make the cable tensions on each side different?
Exactly. If you make the tensions on either side of the bridge different, you change the properties of the medium on either side. That means waves travel faster on one side than they do on the other. And they can never interfere or create a resonance pattern because they can't ever match up. Okay? They travel a little bit faster on one side than they do on the other. If they travel at the same speed, that's when you get this happening. But if they travel at different speeds, you can never get a node and an antinode because there's just never a chance for them to meet up in the same place at the same time over and over again. There might be small incidences of it, but nothing that would ever cause a resonance pattern, which is what happened there. Okay, does that sort of make sense? Okay? If you change the properties of the medium, especially if it's tension in the string, that you change the speed at which the waves travel. Okay? All right. So what we see for a standing wave to form is we have to have that reflection off the fixed end. Okay? And when it reflects, it comes back inverted. The wavelength doesn't change, the speed doesn't change, so they're always going to meet up in the same places, and we're going to get those repeating patterns of interference. Okay, so if I'm looking at a guitar, or any string instrument for that matter, okay, if I pluck the string and I'm not like pinching the string against the bridge, right? Is that what it's called? I never remember that.
Fingerboard, I think.
The what?
I think it's the fingerboard.
Fingerboard. Right. Okay. So the place where you pinch the strings to make the different notes. Okay. So if I don't do that, I'm using the entire length of the guitar string. Okay. When I pluck it, that's the standing wave pattern I would get. Okay. It would oscillate at its fundamental frequency. Okay. It would have a wavelength of what? okay, so this would be half a wavelength, but half a wavelength is 60 centimeters. So the wavelength would be,
120.
yeah, 1.2 meters. Okay, so my wavelength's 1.2 meters, it's producing a frequency of 165 hertz. Okay, from there, I can calculate the speed of the waves on that string. Now, I pluck that, and I don't like how it sounds. It sounds out of tune. So how do you tune a guitar?
Increase or decrease.
Right, you change the tension in the string. You take those little knobs on the end, okay, and you turn them, okay? I don't know what they're called, I just say knobs on the end because that's what they look like. Okay, I turn them and I change the tension in the string, which then changes the speed and thus the frequency of any waves produced after that. Okay? It produces a different sound because I've changed the waves. Okay, everybody all right with that? Okay, if I want to produce a different note, I can change the wavelength. So if I use, instead of this, only half of that string, okay, so I pluck it, or I pinch it right here, and then pluck it, now it's only 30 centimeters long. Well, actually, the wavelength is 60 centimeters, which means it'll have a much higher frequency, because that little bit of string can oscillate back and forth faster than the whole string can. Okay? And that's how I would produce different notes, by pinching the string down on different spots. Okay? I change the wavelength, so I change the frequency. Okay? Now, I think I saw a few people who kind of looked at me like, Coder, before the break, you like really said a whole bunch of times that frequency never changes. That's still true. Okay? Frequency of a wave, once it's produced, won't change. But if I pluck this string and then I pinch it down, those are new waves. The waves I hear now have a different frequency because they're different waves. The waves that were produced before, they keep going on and their frequency will never change. But I change the source by pinching it down here. Okay, does that make sense? So I'm not changing the frequency of waves that are already traveling. I'm changing the frequency of the new waves by changing the source. Okay? All right, now, this is an electric guitar. So it uses a microphone or a pickup, okay, that's going to send the signal to an amplifier that's going to amplify the sound. If you've ever like strummed an electric guitar when it's not plugged in, you don't hear very much. It doesn't make very much noise. Okay? An acoustic guitar, on the other hand, does. So why does an acoustic guitar make a fairly loud sound when you strum it, but an electric guitar doesn't?
Because it has like the hole in it for the waves to bounce on.
Yeah. So when I pluck the guitar string of an acoustic guitar, the guitar string vibrates back and forth. And those waves are disturbances in the air. The guitar string essentially is making compressions and rarefactions in the air. Okay? It's making longitudinal waves that travel into the guitar, okay? Into what we would call the resonance cavity, okay? of the guitar. And in there, those waves bounce around. It's why all string instruments have a similar kind of hourglass shape to them. Okay? That allows for resonance, for a standing wave pattern to form inside of there. The whole body of the guitar will resonate, okay, and produce a louder sound. If you cover up the hole and do that, you don't hear anything, because those waves are not allowed to bounce around inside, interfere constructively with each other, and naturally amplify the sound.
So if you just had like an acoustic guitar that was just like a circle, but
Like a banjo?
yeah, kind of sort of.
Yeah, it would still work. It wouldn't sound the same. Like a banjo obviously sounds a lot different than a guitar. Okay, but I believe a banjo also has more of a tambourine skin over it. Am I right about that? I think that's how it works. So drums also do this, right? So if I hit a drum, okay, near the edge, I get the whole skin to vibrate back and forth. It produces a different sound than if I strike it in the middle, right? Or if I keep my hand on one part and then pat on a different part, I get different amounts of the skin. That's why different drums have different sizes, right? Your bass drum is huge, okay? Whereas your snare drum, which also is a bit different, your toms, I think that's what they're called, right? The smaller ones, okay? They're smaller, so they produce a higher frequency of sound than the bass drum does. Yeah? Yeah, so same idea. And all musical instruments rely on resonance, making a column of air resonate. Okay? Okay, so we're going to talk about resonating air columns here next, but I got to get one set up because I don't have it ready yet. So I'm going to give you guys a little break here while I go get some water and my air column and some tuning forks.
Can I go to
Yes, you can. Okay, so here's what we're gonna do. We're gonna look at the first type of air column, because it's the only kind I can really replicate very well, okay? And that is a closed air column, okay? In a closed air column, okay, I have a column of air that is closed at one end, okay? So that means any waves that go in will hit that end and they'll reflect off of it and they'll come back out. If I make that length, the column of air the right length, I could get an antinode at the top. And I would hear what kind of a sound? If I have an antinode?
Loud?
Loud, yeah, right? So here's a standing wave, right? Like on a spring, this is the antinode and that's the antinode. Okay, that would be loud if this was a sound wave. Right? Well, the same thing happens inside a column of air. All right? The first pattern that I'm going to get in this column of air is going to look like this. Okay? Actually, I'll use a different color so you can kind of see the difference here. Okay, so the first column or first wave pattern is going to look like that. So my antinode will be right there at the top. Okay? How many wavelengths are there? A quarter, right? Because I'm going from here to here, right? So that's 1/4 of a wavelength. Okay? Now, we know that the temperature in here today is 22 degrees. All right? So what I'm going to do is I'm going to use a tuning fork and that apparatus right there, that column of air, to calculate the speed of sound in here. Now, according to our formula, the speed of sound in air in here today should be 345.2 meters per second. All right, I'm going to use that apparatus to check that. Okay, the things I'm going to be able to measure are the frequency, because I'm going to use my favorite note, C, okay, which is 523.2 hertz, because everybody knows that. Okay, so I'm using a frequency of 523.2 hertz. And what I'm going to do is I'm going to figure out how long my air column is when this happens. What will I be able to use that to get? Yeah, because that'll be 1/4 of a wavelength. And then I'll be able to get the wavelength from there. Everybody okay with that? Okay. Okay, so you'll be able to hear this no problem when it gets on. Okay? So that's what the tuning fork sounds like normally. Okay, I'm going to hold it over the tube so you can hear what it sounds like before I get the tube moving. You guys hear it? Mm-hmm. Okay, so the column there was 0.15 meters in length. Okay, is there a possibility I could get more spots like that? Okay, so where do you suppose the next one would happen?
3/4.
At 3/4, yeah, because at 1/4 I got one. At 3/4 is the next antinode, right? So for my next trick / resonance point, okay, I should have this in the tube. Right? 3/4 of a wavelength, which should be how many times longer than this? 3 times. So about 45 centimeters. Okay? hold this closer to Joan so you can read it. Because once it starts to get tall, it's hard for me to read. What's it read? Where's the water level?
Oh, water level, 49.
Try it again. That's a little big. I don't doubt your reading, I doubt my holding.
We're like 48 now.
48 now. We're not gonna get much closer. Plus, there's also the nature of the water trying to hug it a little bit because it's polar. Okay, so 48. Ooh, it's like over there. Okay, 0.48 meters. Do you suppose I can get another one? Okay, it happened at 1/4, at 3/4. Where's the next one? Yeah, 1 1/4, 5/4, right? 1/4, 3/4, 5/4. Okay, so the next one should have 1 1/4 wavelengths in it. So but it would be more symmetrical than that. Okay, so that should be the next one, and that should happen at 75. Yeah, 75, or around 75, somewhere in there, right? With ultra.
I can't read it.
Oh, if I turn it toward you, it's easier.
That was like 82.
82, yeah. Okay. That's all right. We'll just try and see if we can get it a little bit more accurate.
Still about 82.
82, okay. All right. All right, that's probably all we'll get. We might be able to get the 7/4, but I doubt it. Okay. All right, so this length represents 1/4 of a wavelength. Okay, so that means that one wavelength should be agreed? Right, 4 times that number, okay, that should equal lambda. Okay, this was 3/4, so 0.75 times lambda. So if I divide this side by 0.75, will that give me lambda? Okay. .64, okay. Right, and this one equals 1.25 times lambda, right? 5/4. Everybody okay with that? And so if I divide this by 1.25, that should give me the wavelength. So 0.66. That's usually what happens when we do this. Okay? All right, so that means if I average those, okay? So that's what I'm going to do, is just going to average those. So plus 0.64 plus 0.63. All right, so that's our wavelength, 0.63 meters. Okay, everyone okay with what I did there? Okay, so if I take that, that's now my wavelength. I know I use this frequency. Should I be able to calculate speed?
Yes.
Using the universal wave equation, okay, which we talked about before Christmas. All right, so if I take the universal wave equation, I take that number and I multiply it by 523.2, which was the frequency of sound I used. Okay, I get 330. That's not great. Okay, I probably did something a little bit wrong when I did this, but, okay, it's as accurate as I can be. Maybe my thermometer is out over there. Okay, but I get a reasonable number for the speed of sound, right? Everyone okay with that? Okay, so that's how a closed air column works. Okay, the sound goes in, it reflects off of the surface, in this case it's water, okay, and it comes back out, and at certain lengths, you'll get that resonant point. It's how you make noise if you're blowing across the top of a bottle. Okay, if you've ever done that, you blow across the top of a bottle, you get a sound, depending on how full the bottle is, the sound changes. Because you're going to get a standing wave pattern, you're just going to get longer and longer waves the more and more empty the bottle becomes. Okay? Or if you've ever done that thing, maybe you did at Christmas, okay? If you have like a crystal glass and you wet your finger and you go around the rim of the glass like this, you can get the crystal to hum. Okay? It hums differently depending on how much air is in the goblet part. Okay? The longer that column of air, the longer the waves, the lower the frequency of the sound you get. Okay? The closer to full, the higher the frequency. Okay? Like there's people out there who like set up different glasses and they like play music. Okay? Using the different notes that they can produce. Okay? Everyone all right with that? That's closed air columns. Okay? Open air columns work differently. Okay, so in a closed air column, this is what we got. So this is a much better diagram than I drew. Okay? Our first standing wave pattern occurs with 1/4 of a wavelength in the tube. That is our fundamental form. Okay, right there. Okay, the second one would be 3/4, 5/4, 7/4, if I could go that far. I was using the shortest tuning fork. We probably could have got all of them, okay, but it would have been tough because I'd had to stand on the chair, okay, for the last couple. All right. We used to do this as a lab, okay. You can see how badly this one's leaking. And do you notice I never, ever lifted it off the floor? I did this every time. Well, we used to do this. Like this. You know why we stopped? People would pick this thing up off of the desk and the stopper would come out at the bottom. Where does the water get you? Yeah, it makes you look like you peed your pants. Happened like 3 times, and then we stopped doing it because people had to walk around looking like they peed their pants all day. Okay, and so we stopped. All right. I actually demonstrated the whole like thing happening last semester by accident. It actually just came right out on me. All right. That make sense? It was pretty funny. I can laugh at myself. Okay. All right. So that's for closed air columns. Very few musical instruments, with the exception of string instruments, are closed air columns. Okay, like a guitar is a closed air column. There's only one hole. Okay, but most of your wind instruments are open air columns. They have 2 holes. Okay, so air can go in and out both ends. All right, so things work differently there. But for fundamental frequencies, for closed air columns, our wavelength is 4 times the length of the tube, okay? Because at that first resonant point, you get 1/4 of a wave in the tube, okay? Now that formula is on your formula sheet, okay? That's the closed air column formula. It doesn't say that on your formula sheet, okay? You have to remember that closed air columns at their first resonant point are 1/4 of a wavelength, or lambda equals 4L, okay? All right. Now, on this one, this was F1, and this was F3. This was F5, and this was F7. Why don't I have any even numbers?
Because that would mean destructive.
Exactly. They're nodes, right? We got them. You just don't hear it, okay? You'll be able to hear when I pass them. Like you can hear the loud ones, and then you can hear the quiet ones. Okay? But it's much harder to pinpoint where a node is than an antinode, because you can hear when the volume gets louder when it's at its loudest, but it's hard to hear when it's at its quietest because you still hear the actual tuning fork. Okay? So a closed air column actually doesn't resonate at even numbered frequencies, because at F2, what I would have is this. I'd have a node at the top, not going to make any sound. Okay? It's not that there isn't sound, there's a wave in there. I just have a node at the top of the tube, and I have one at F4 and at F6 and at F8 and so on and so on. So closed air columns can only resonate at odd harmonic frequencies. That means that their musical range is shorter, smaller. Okay? They can't produce as many notes as an open air column, which is why more of our wind instruments are open air columns. They produce a wider range of sound because they can resonate at all of the frequencies. Okay? All right, everybody okay with that setup there? Okay. So open air columns, as their name would imply, are open at both ends. So the waves actually reflect off the inside of the tube, not off the end. Okay? And what that produces is nodes at both ends at all frequencies. So this would be F1. How many wavelengths are in the tube? Half, yeah. Okay, like if we draw a full, well, not like that. Okay, if we draw a full wavelength like this, okay, we've got between here and here in the tube. That's half a wavelength. Okay, so we've got an antinode at each end and we get a sound. Okay, this is F2. Well, at F2, we've got a full wavelength in the tube. Okay, here's a quarter, here's a half, there's a quarter. That's full wavelength. Okay, that's at F2. So you'll probably notice that resonant points are always half a wavelength apart, even in the closed air column. 1/4, 3/4, 5/4. They were always a half a wavelength apart. Okay, same is true here. It's just because we get antinodes at both ends all the time, we actually get sound at all of the frequencies. There's never a condition where there's a node at each end.
With the piano, like, that's a closed column?
Yes, it would be. And then its shape is what, well, the strings are in there, right? So it has, a grand piano has that shape because it's got the shorter strings at one end and the longer strings at the other. And then, yes, the column of air, and when you open the lid, the vibration reflects off the lid, right? So you face the lid, open lid towards the audience.
Oh, okay.
Yeah? And if you have the lid closed, the whole body will resonate. Yeah.
So do nodes like completely cancel out the sound?
Yeah. That's why, like, I mean, we still heard a sound when I was doing it there because the tuning fork was still making sound, but the column didn't make any noise, right? That's why the volume just kept going down, down, and then it came up again as it got past it. Okay? Everyone all right with that? So, at our fundamental frequency for an open air column, lambda equals 2L. For the closed air column, it was 4L. Okay? But for this one, it's 2L because there's half a wavelength in the tube. The length of the tube multiplied by 2 would be the full wavelength. Whereas in the closed air column, the length of the column multiplied by 4 gave me the full wavelength. Okay? Everybody all right with that?
And that L is the length of
This is the length of the column, right? Okay, so where you would see this in wind instruments would be, like a trombone is a great example, okay, of lengthening the tube, right? So you lengthen the column of air by pushing the slider out, you get a lower, right? You pull it in, you get a higher frequency because the column of air gets shorter, okay? With the other wind instruments, it's you press different keys or buttons, okay, and you let air out a different place. You change the path of the air so it changes the length of the wave that it produces. Okay? And obviously, when you're looking at string instruments, the size of the body of the instrument is indicative of the sounds it can produce. Like a big bass, okay, it's really, really, really big. A tuba produces low sound because it's really, really big and long. Okay? A French horn, or a trumpet is much smaller, shorter.
Isn't like a harp, that's an open, because it's like, there's.
The harp is just pure string. There's no, you're just making the air around resonate.
Okay.
Yeah, there's no column there that's causing anything else to
Okay.
happen.
I know the logic.
Yep. Okay, everyone okay with that? And like I said, drums, same thing, right? You bang on a drum and it's the length of the size of the skin, right? That can do that. Okay. I don't like that question. I hate the way those are worded. Okay, let's try this one here, all right? So just, this one's actually in your workbook, so I'm just gonna go over, you don't have to write it down because it's in there. Okay, so in this case, I have a closed air column, okay? So as soon as I see that it's a closed air column, I know that lambda equals 4L, okay? That's the thing you have to memorize, okay? The formula is on your formula sheet, you just have to know that one's for closed, okay? And its fundamental frequency, F1, is 256 hertz. Okay, what's the length of the air column if the speed of the sound wave is 343 meters per second? Okay, so I'm looking for L. What do I need? I need lambda. All right, how will I get lambda if I have V and F?
You would manipulate your speed equation.
Right, use the universal wave equation. Okay, V equals F times lambda. Okay, I'm looking for lambda, so I divide both sides by F. Okay, and I'll take my 343, divide it by 256. That'll give me my wavelength. Okay, so 1.3 meters. Okay, is my wavelength. Now I can plug that into this formula, oops, to get my length by dividing lambda by 4. Right, so I'm just going to move the 4 over. Okay, so lambda over 4 equals L. Okay, and so okay, so 0.335 meters would be the length of that column of air, okay, which is very close to the one we were using. Okay. No, sorry, half. It was half the one. Okay, does that make sense? So air column questions really just involve you having to visualize what the column of air looks like and use the universal wave equation and this. So you're either using lambda as 4L or lambda as 2L. Okay, the questions could ask you about length. It could ask you to calculate the speed of sound. It could ask you to calculate the frequency of the sound. Okay, any number of things. Now, for this particular column of air, it made its fundamental frequency was 2.56 hertz. Okay, what's the next frequency I would hear?
It would be 256 times 3.
Times 3. Okay, remember, this is a closed air column. Okay, right now we're hearing that waveform. F2 doesn't make any sound. I wouldn't hear anything. This is a trick that can come up with closed air columns. A lot of times in a closed air column question, the part B would be, all right, you calculated what the fundamental frequency is. What's the next frequency you would hear? Well, it's not F2, it's F3 because it doesn't make any sound at F2. Okay, so I've multiplied 256 by 3 and that would be the next sound I would hear. Okay. All right. Closed. Open. Okay, let's do this one just so we get an open one. Oh, that's bad luck. I should change that question. Okay. So we have an open air column. So as soon as I see that it's open, lambda equals 2L, okay? Assuming it's fundamental, and that's what I would do. Okay, fundamental frequency of 256 hertz again. Okay, we are looking for the length of the air column if the speed is 341 meters per second. Okay, am I doing pretty much the same thing I did for the last one we did? Okay, so I got to find out what lambda is. So V over F, 341 over 256. So that'll be our 1.339 again, okay? And so 1. Okay, and then I would find that length by simply dividing that by 2. So lambda over 2 would equal L. I must not have carried all my decimals over. Okay, so I get 0.670 actually on that one. Oh, no, I don't. 341. Yeah, 341. 341 divided by 256. And then I divide that by 2. That's going to give me that. Yeah. Okay. Am I all right with that? Okay. Are those questions terribly difficult?
No.
Not really. I mean, the context might get a little tricky sometimes. Like, as an example, on an exam I once gave a question where I was talking about a wine glass that was partially filled with fluid. So I said the wine glass was like 10 centimeters tall, but it was 1/4 filled with wine. So how much air is there? Right, 7.5 centimeters. That's like little contextual tricks that I can play. Remember, it's only the column of air that resonates. It's reflecting off the liquid.
But with the
Okay.
wine glass, do you have to take into account like the stem of the wine glass?
No, because the stem isn't the part that resonates, it's the air. You make the crystal
Oh, so
vibrate.
you're talking about like the length, you were just talking about the
Oh, yeah, just the
cylinder,
goblet.
not the actual, yeah.
Yeah, and I had a diagram so it showed like
Yeah.
this. Okay, but there's little things like that, there's little contextual tricks. Okay, so we will talk more about that tomorrow, and then we'll do Doppler effect on Wednesday.